Modeling support reactions in 3 dimensions is certainly harder than doing it in 2 dimensions, as there's twice as many potential motions that we have to consider, either the forces or the moments that that support is going to provide. However, the general rules for modeling are going to be the same in 3D as 2D. So still, we have to consider when we remove the support from our object of interest that we are modeling what that support does to the object that we kept. We can still have ropes and cables in 3 dimensions, and they're going to behave the same as in 2, that they are always going to act along their length. But in general, we have to consider what motion was prevented because that support was present on our object. And as with 2D, we're going to consider it one support at a time. However, each support, we have to think now in terms of translation. Did this support prevent translation along an axis, in a plane, so it would have 2 components of force, or does this support prevent translation in space, in which case it will have 3 components of force? In terms of rotation, now we can rotate about any of the coordinate axes. Does it prevent rotation around 1 axis, 2 axes, 3 axes, preventing all rotation? Well, that's going to tell us how many couples it's going to introduce and about what axes these couples will act. As with 2D, the best strategy for modeling these supports is not to memorize just a list of supports, but to really consider what motion is prevented because that particular support was there. And that's how it's going to appear in the free body diagram with the appropriate forces and the appropriate couples. So as a recap, if the support is preventing translation on a specific axis, in a plane, or in space, we're going to put forces from that support on our object along those axes, or components in the plane or components in space. We can also have normal forces where we're going to know the direction of that force is always out from the surface. And we're going to see here if we don't know the particular direction of a force, but we do know along what axis it is acting, we can just, for the sake of easiness in the math, assume that it's going to be acting in the positive direction. And then we're going to let the final mathematical results tell us, was our assumption correct or incorrect? Was it actually facing the opposite direction? The assumption of the positive direction is really just done for consistency and simplicity, and we're not necessarily thinking that forces are going to be acting along that positive direction, but we're going to let the negative or positive sign at the end tell us. And now we have to think about rotation, about 1, 2, or 3 axes. Is it prevented because of the support? Usually with supports, if it's going to prevent rotation, it's going to prevent it clockwise or counterclockwise. So once again, the easiest assumption to make is going to be that it's acting positive around an axis in the counterclockwise direction. And as with forces, we're going to let the sign on the couple tell us if our assumption of counterclockwise was correct or not. A negative sign will indicate it's actually clockwise around that axis, and our assumption was not correct. So now we'll go through some of the common supports that we're going to encounter in 3D. But again, I want to reiterate that the best strategy is to always think about translations and rotations that are prevented by a support in order to know how to model it in the free body diagram. Like we saw with particles, we can have a rope or a cable acting on a point, and we know that it's going to provide a tensile force along the direction, along the axis of that cable or rope. We can have a smooth surface support. Here we are going to be neglecting friction, so we're assuming that there's no forces that the ground is imparting parallel to the surface, only a force perpendicular to the surface. And here, this is really just a normal force, and we know that it has to be out from the surface of the floor in this case, or the surface in this case, because the surface can't grab onto our object, it can only push on the object. So we know the direction of the axis is the normal direction to the surface, and it must be outward. Really the same idea when we have a roller. We're typically going to model rollers as also being friction-free and only preventing motion that is normal to the surface. So a roller is going to act just like a normal force, outward normal from the surface that it is in contact with. Now what's new in 3D is we're going to see the ball and socket. Again, we're going to consider what is prevented. Well, this object we can't move in the plane of the floor. We can't move it in what we can call the X direction or the Y direction because it's connected via the ball and socket. We also can't move it vertically in Z. We can't move it or translate it specifically anywhere in space. So what we can do there, because all spatial translation is prevented, we can model that as components of force along our coordinate directions. So again, we're doing this for simplicity, and we're doing it so mathematically it's going to be easier to solve for the components of this force. In reality, though, it is one force along one direction, but it's going to be harder to solve for that force with two angles than it is to put it into these Cartesian components right away. Now, when we think about the rotation, the ball and socket is not preventing any rotation. And again, we want to think about small translations, small rotations, when we're considering the reaction forces and the reaction couples. So can we rotate it around the, let's say, the x-axis? Yeah, we can freely rotate it along this direction. It's not going to stop us, at least if we rotate it a little bit. Now, if we try to do a 180-degree rotation around that x-axis, it's going to hit the floor. But that's not what we're considering. Because we're in static equilibrium, it's just going to be small movements. What about the y-axis this way? Well, if we try to rotate it around that y-axis, again, nothing's going to stop us there. And the z-axis, if we try to rotate it this way, the ball and socket is not going to prevent that either. Typically, we're going to ignore that there might be some friction between the ball and the socket, so there would be some resistance there. But we're, for the most part, neglecting friction, especially now, until we talk about impending motion later in the course. Similar to a ball and socket, we can have a pin. Now, the pin is going to behave a little bit differently because here it is going to prevent all spatial translation, just like the ball and socket did. We can't move up and down in the x direction, along the y direction, because it's connected to that pin. However, the pin is made so that it can rotate around what we're calling this x-axis. So the axis parallel to the pin, we can rotate around at least a little bit. That's kind of the purpose of the pin. But if we think of this y-axis, if we try to rotate it about this axis, so a rotation this way, well, it's going to stop that because the pin is there, and the pin is not going to allow it to rotate along this y-axis. Same idea around the z-axis. The pin connection is going to prevent the free rotation around z. So this pin prevents all spatial translation, so that's going to be x, y, z components of force that we see over here, and it prevents rotation around what we have designated the y-axis and the z-axis, but it allows rotation around what we're calling the x-axis. So if we look at how we model it in the free body diagram, 5 reactions, 3 components of force, and 2 components of moment. Notice in particular there is no m sub x. It allows rotation around that x-axis, so there is not going to be a couple about that axis. Then we have a hinge, which is really going to act just like a pin. It's just kind of a wider pin there, so it's the same idea of the forces and the moments. It is able to rotate in this picture around this axis. They're calling it the y-axis. So we notice in our free body diagram for it that there's no moment around y. However, it cannot rotate around this z. It cannot rotate freely around the x. And all translation is prevented as well. So also in this picture, 5 components of reaction. And finally, in this picture, we have our fixed support. So this is kind of like that built-in connection we saw in 2 dimensions. When it's fixed or built into the ground, we cannot translate it anywhere in space. So that gives us those 3 components of force. And also the fixed support, we cannot rotate it about any axis because it's built into that surface. We can't go around the z, around the x, or around the y. All of those rotations are prevented. So we see here for this fixed support, we have 6 components of reactions, 3 force components and a moment component about each of the axes. So a fixed support prevents all motion at that point. And also commonly we're going to see bearings when we are in 3 dimensions. And we're going to see kind of two types of bearings. So we have here, I put a table together that describes the difference between them. So let's go in the columns first. So a bearing can be what we call a journal bearing or a thrust bearing. And for the purposes of this course and both of the textbooks, if a bearing is simply referred to as a bearing without the description of journal or thrust, we're going to take it as a journal bearing. So what's the difference between a journal bearing and a thrust bearing? So in a journal bearing, if we look over at this picture here, the journal bearing is going to prevent the shaft that runs through it. It's going to prevent it from moving normal to the axis of the bearing. So we can't have a motion, let's say this is the z-axis, that's prevented, and let's say the y-axis, that motion is also prevented. However, the shaft can freely move along what we'll call in this picture the x direction. It's not preventing that. So we're going to have a z force, or a component of force in the z, and a component force in the y, because those translations are prevented. However, no force along the x direction, that is allowed in a journal bearing. In contrast, a thrust bearing is going to do what a journal bearing did. There is no motion in the z allowed or the y allowed, but in a thrust bearing, the shaft also cannot freely move along its own axis. So there would also be a component of force along the x direction. So a thrust bearing is going to prevent all translation of the shaft, whereas the journal bearing is only going to prevent translation normal to the axis of the shaft itself. And a bearing can also have the property of being either called self-aligned, or a set of bearings are properly aligned, or we might have no information about the alignment. And in this course, almost always we're going to be dealing with self-aligned or properly aligned bearings versus bearings that we don't have the information for or are explicitly not self-aligning or properly aligned. So what's the difference between these two properties? So in a self-aligned bearing or a properly aligned bearing, what's going to happen there is there's going to be no rotations that are prevented by the bearing itself. So for most bearings, at least circular bearings, we want the axis to be able to rotate around its own axis, or the shaft to rotate about its own axis. For most bearings, that's the point. Maybe not the square bearing is an exception to that, but for circular bearings, we want it to be able to rotate around its own axis. However, we're probably not intending for it to rotate around, again, let's call this the z-axis, to rotate around that axis, or the y-axis. We probably are not intending it to really rotate around that axis. If we have a self-aligning bearing, what that means is that the shaft is able to rotate a little bit, at least, around the z and the y direction. Again, we're talking about small rotations here. In a bearing where there's no alignment information, then the bearing itself is going to be preventing that rotation, even if it's just a little bit, and the bearing will impart a moment around the z-axis and the y-axis on the shaft. So as far as moments go, self-aligned, properly aligned bearings do not impart any moment on the shaft, whereas if we don't know anything about the bearing, we will have moments that are around axes normal to the axis of the shaft. So to summarize, a journal bearing versus thrust bearing is really talking about the forces that are going to be imparted. A journal bearing, two components of force, normal to the axis of the shaft. A thrust bearing is going to prevent all spatial translation. If we're talking about the alignment, self-aligning or a set of properly aligned bearings provide no couples to the shaft, whereas no alignment information, we're going to have to assume that the bearing is imparting two couples on the shaft that are normal to the axis of the shaft. Now, as far as bearings go, applying couples, it is typically not good if the bearing is going to be creating a moment on the shaft itself. That is how a bearing will get damaged, or a shaft is going to get damaged. So that's typically why we don't want to be dealing with bearings that are not self-aligning or a set of bearings. Now, proper alignment means that if we have a bearing here and then maybe a bearing further down the line, proper alignment means that the shaft itself is not wanting to rotate around this z or this y axis. If they're properly aligned, they're perfectly in line here, and the shaft does not want to rotate about any axis other than its own.